Hi, I'm Tomáš Iser from Charles University, and today I will show you a really simple way to describe the appearance of translucent materials, which can be used to measure their optical properties without any sophisticated and expensive laboratory equipment. Say you are an artist and you work on visualizations and photorealistic rendering. Many materials in the world are translucent. This includes almost all liquids, but also many solids like plastics, glass, wax, or wood. Even when you play with a flashlight, you probably notice the translucency of your own skin. In order to simulate this appearance, you need the material's optical properties. This includes the extinction coefficient, single scattering albedo, and phase function. And this is exactly where our new measurement method shines. It allows anyone with a tight budget to construct a simple setup in which a sample can be placed, and its scattering properties can be estimated with a high spectral resolution. This results in high color accuracy and avoids various problems of RGB rendering, which we can hopefully consider outdated. So our method is useful for photorealistic rendering, but our main motivation was actually in 3D printing, which is a related problem. In color 3D printing, we start with a set of base inks. Microscopic droplets of these inks are deposited into a three-dimensional grid, which is solidified. In the end, we get beautiful, colorful objects straight from the 3D printer. Unfortunately, light scattering within the ink layers negatively impacts the printing quality. Fortunately, research papers in the past have shown that this can be significantly improved by iteratively optimizing the ink distribution. And in order to do that, the ink's optical properties need to be measured. Again, our method offers a perfect solution to this problem. So what would you do if you had a piece of translucent material that you would like to render? If you had never seen this video, you would probably try to find the previous publications on this topic. We have done this homework for you, and we tried to categorize the methods into 3 groups. The first group uses goniometric setups. In these, you shine a collimated beam of light onto your material. This light scatters around, and you detect it from various angles. The obvious drawback is that you need rotational stages that will allow you to rotate your sensors around the sample. And no matter how much automation you use, you still need accurate calibrations and precise optical equipment. That gets expensive. The second category uses integrating spheres. And here you can see a setup with 2 of them. You shine a collimated beam onto the material, and some of the light scatters backwards and some forwards. This light is collected using the spheres connected to 2 spectrometers. You can also use a third spectrometer to detect the unscattered transmission. Unfortunately, integrating spheres are expensive because their interior is coated with a highly reflective material. The third category are setups that do not need any sophisticated equipment. They are based on taking a single photograph of the material illuminated in a specific way. From these photographs, we take a line of pixels, which gives us a one-dimensional brightness curve. This curve shows how the light intensity changes spatially due to light scattering. You can do this in several different configurations, such as using an aquarium with a diluted liquid and a light bulb, constructing a custom container with several LEDs, or placing the material on top of a checkerboard pattern. The flaw here is the camera capture. A typical camera only captures a photograph in RGB, so you cannot get spectral data out of it without sophisticated hyperspectral solutions. With a spectrometer, you can only measure a single point. Can we estimate light scattering from only a point measurement? The answer is yes, and our paper shows you how. We start by constructing a translucency appearance map. Look at this picture. There are 3 cuvettes with the following materials: water, red wine, and milk. Behind these cuvettes there is a black and white wall. Now look at how the 3 liquids appear against the black background. Both water and wine appear black, but milk appears white. How is this possible? Milk scatters light, and so the light bounces towards the camera before it even reaches the wall behind. When it comes to the white background, clearly the red wine is the only material through which the wall is not white. That is because red wine is only translucent for red wavelengths, and it absorbs the others. These incredibly simple observations already give us enough information to judge the absorption and scattering of the materials. At this point, we decided to simulate this scenario on a computer using Monte Carlo. The goal was to try different optical properties to check if we could see some pattern in the light's behavior. We initially ran about 8,000 simulations, which took a couple of hours on a dual CPU computer. And we were positively surprised by the result. We decided to call this the appearance map. The horizontal axis shows how bright the material appears on the black background, and the vertical shows the brightness on the white background. And then we can see several contours which represent a subset of our simulations. The green to cyan contours connect all materials that have the same albedo. There are several contours, 1 per each albedo, ranging from 0 to 1. The blue to purple contours connect all materials with the same extinction coefficient. This allows you to locate a material with given optical properties and see that its brightness against the black background is about 40%, while on the white background it is about 80%. This appearance map is a crucial result of our work because it visualizes the relation between appearance, which we can see with our own eyes, and physical properties, which we cannot directly observe. I will now show you how the map behaves. For starters, notice how nothing appears in the bottom right triangle, because such appearance cannot be achieved with any common material. So how about the diagonal? All materials along the diagonal are perfectly opaque as their extinction coefficient approaches infinity. The position along the diagonal changes the albedo, influencing the material's brightness. Along the left edge, we have non-scattering materials with 0 albedo. The top edge has purely reflecting materials with no absorption. And finally, everything in between represents both absorption and scattering at the same time. What you have just seen is the behavior of monochrome materials. So what about colors? The key property of the map is that it is wavelength independent. We only need to simulate it once and then apply it to each wavelength in the same way. Colored materials that have spectrally varying properties simply have a different position in the map for each wavelength. Here is an example of a blue scattering object. It is strongly absorbing red wavelengths, so they are at the bottom of the map. The blue wavelengths are higher in the map because these are scattered by the material. What would happen if we move the blue wavelengths towards the left of the triangle? Suddenly, the subsurface scattering would be reduced, making the object clearer. This shows that the appearance map encompasses all possible materials of various colors and translucencies, and it is perfectly suitable for spectral workflows. So far, we have focused on the albedo and extinction coefficient, but could we also include the material's phase function in the appearance map? Let's have a look. Here we can see data points of an isotropic phase function in blue and of a forward scattering phase function in orange. Clearly, the data points overlap, so we cannot discriminate which phase function a material has just from this two-dimensional map. In our paper, we expand the map to 3 dimensions to address this problem. To the existing 2 axes corresponding to the 2 backgrounds, we add a third one representing the transmission of a collimated beam. Here, the 3-dimensional contours correspond to different phase functions, and they no longer overlap. More information on why and how the map works in 3 dimensions can be found in the paper. Let's now look at our second contribution, which is using the appearance map for measurements. I will show you the components that build the whole physical setup. For starters, we need a strongly absorbing black material and a strongly reflecting white material. We used a black flock paper and a small spectralon, but a cheaper alternative would be a white PTFE sheet. The measured material is then placed right in front of the backgrounds. Solid samples need to be optically smoothened in a sandwich of immersion oil and microscope slides. The sample is diffusely illuminated. We showed that even 2 cheap LED panels provide very good results. The light that is scattered back from the sample is focused into a spectrometer. The spectrometer captures spectrally resolved brightnesses against the 2 backgrounds. Using the appearance map, we can then look up and interpolate which albedo and extinction correspond to such material. To also estimate the phase function anisotropy, our setup needs to be extended to measure the 3rd dimension of the appearance map. We do that by placing and collimating an LED behind the sample. Okay, let's use this setup to measure some real materials and see how it performs. We tried our method on the base inks for 3D printing. Several test samples of various thicknesses were printed from different ink sets. This picture shows measuring a thin magenta sample against the white background using our custom background holder. You can also see a very important element of the measurement. The rough surface of the sample is smoothened by the immersion oil and microscope slides. In the end, the process results in spectrally resolved single scattering albedos, extinction coefficients, and phase function anisotropy for each of the 5 inks. Our light sources cover the range of roughly 400 to 700 nanometers, which is sufficient for color accuracy. Here you can see an example of the magenta ink's albedo. As expected, it increases towards the red wavelength. To improve accuracy, we measured 2 samples of different thicknesses and combined them into a final estimate represented by the black curve. Now let's see how we verified the accuracy of our results. We decided to 3D print a color checker containing 64 combinations of base inks. For example, in the bottom right corner, we can see a gradient of varying black and white ink ratios. The color checker was printed using the same inks that we have measured using our method. Assuming the optical properties are correct, we simulated how the color checker would look like. We then compared the spectra of the virtual color checker to the real physical one. A subset of these verifications is available in our paper. And here are a few notable examples. We start with the base colors, where the measured curves, which are blue, and the simulated curves, which are red and orange, have very similar shapes. The colored rectangles then show the sRGB colors corresponding to the curves. This is a satisfying match where no differences can be seen. For clarity, I will also show a few ink combinations which displayed a lower quality of the spectra. Even then, though, the corresponding sRGB color predictions are close to the reference colors. To sum up, the key discovery of our paper is that bulk optical properties can be estimated from only 3 simple point measurements with a single spectrometer. This allows more accurate measurements with affordable setups that anyone can build at home or work. A byproduct is the intuitive appearance map, which might find its future use in interactive material modeling or education on translucency. In the future, we would also like to further explore some inaccuracies which we believe to be caused by fluorescence. Expanding this setup to also measure fluorescent materials would be a huge benefit. Thank you, and until next time, see you.